This tutorial is brought to you by PE Prep Engine. Free study guides and practice questions at preprepengine.com.
Week 4, Lesson 8, Energy Recovery. An air-to-air recovery unit pre-tempers incoming outdoor air using the air you're already throwing away, so it's near-free heating in winter and pre-cooling in summer. The key idea is that every device, wheel, heat pipe, runaround loop, plate exchanger, rides one effectiveness framework. We'll number the 4 airstreams, build the HRV and ERV effectiveness relations, then work a winter HRV example. Concept 1. One framework. 4 devices. A recovery unit warms incoming outdoor air with the exhaust you're about to dump. The device only decides what moves. An enthalpy wheel or a fixed plate ERV moves heat and moisture, so it carries a total effectiveness. A plate HRV, a heat pipe, and a runaround loop move heat only, so they carry a sensible effectiveness. The handbook does not size these separately. One effectiveness set covers all of them. Concept 2. Number the airstreams first, because every formula depends on it. 1 is supply in, the outdoor air. 2 is supply out, headed to the space. 3 is exhaust in, the return air. 4 is exhaust out, dumped outdoors. Supply and exhaust cross in opposite directions through a single counterflow core. State 1, the outdoor air, and State 3, the return air, set the driving difference for every effectiveness. Setup, Part 1. The HRV, a sensible-only device. Sensible effectiveness is the temperature swing the supply actually gets, divided by the maximum available. From that one definition come the maximum sensible rate, a leaving supply temperature, and the recovered rate, all on one page. C-min is the smaller of the 2 stream capacities, and the 60 converts the CFM-based mass flow from per minute to per hour. Setup, Part 2. The ERV. Because a wheel or fixed plate core also moves moisture, its effectiveness is written on enthalpy, not temperature. The total effectiveness is the supply enthalpy swing over the maximum. A moisture effectiveness tracks the humidity ratio swing, and a separate latent effectiveness covers the latent part alone. Don't forget the recovery fans themselves cost power. 1 term per stream. Solve. A winter HRV, balanced flow, effectiveness 0.7. Outdoor air enters at 10, return air at 70. Leaving supply is the inlet plus effectiveness times the driving difference, 52 degrees. For the recovered rate, the mass flow is the airflow times density, and the 60 effectiveness mass CP form gives roughly 91,000 BTU per hour of otherwise wasted heat, put back into the supply. Traps. 5 ways this bites. 1. Sensible effectiveness is on temperature. Total is on enthalpy. A wheel moves moisture, a heat pipe does not. 2. Always divide by the smaller stream, M-min, not the supply stream. 3. Use the long 60 row CP form. Don't drag week 2's 1.08 shortcut into this. 4. Keep the numbering straight. 1 is supply in, 3 is exhaust in, and the driving difference is always 3 minus 1. 5. Match the device to the effectiveness. Wheels and fixed plate cores give total. Heat pipes and runaround loops give sensible only. Quick recall. Number the 4 streams, supply in and out, exhaust in and out. A sensible device like a heat pipe or plate HRV uses the temperature effectiveness. A wheel or fixed plate ERV uses the total enthalpy effectiveness, and the fans cost power. Golden rule. Number the streams first. Divide by the smaller flow and reach for enthalpy on a wheel, temperature on a heat pipe. Next up, Lesson 9, the air side pressure budget and balancing. We assemble a whole duct system, walk the critical longest pressure drop path, sum the friction and every fitting loss coefficient section by section, then size the fan to that path. Everything's at preprepengine.com. Cheat sheet, worked solution, and a quiz attached here. If the course helps, subscribe.
The full study guide with every equation and common exam trap is free at preprepengine.com, link in the description. Structural, civil, and electrical series are coming soon. Subscribe so you don't miss them.